Myself, Sridhar KN, Assistant Professor of Physics, Government First Aid College, Kolar. I am taking session 19 of second BSc third semester of Bangalore North University. The title of the paper is Electricity and Magnetism. The unit is Magnetic Field and Forces, and session 19 corresponds to magnetic field due to a straight current carrying conductor. The learning objectives are the students understand the concept and derivation of the expression for the magnetic field due to straight current carrying conductor, and the session outcome will be students understood the concept and are now in a position to derive the expression for the magnetic field due to a straight current carrying conductor. So coming to the topic magnetic field due to a straight current carrying conductor, we have considered a straight current carrying conductor of infinite length, where O is the midpoint of the conductor. The total length of the conductor is taken as 2L, or on one side from the midpoint it is taken as equal to L, where L is equal to infinity for one side. In this long conductor, in this long, infinitely straight long conductor, we have considered a small element dl, shown over here. We have considered a small element dl, and this element, or let this conductor carries a current I. Let this conductor carries a current I, where I is the magnitude of the current flowing through this conductor. And the product of I and dl is called current element. The product of I and dl is called current element. From the midpoint of dl, we have considered a point P. We have considered a point P over here, which is at a distance r from the midpoint of dl. We have considered a point P where we require the magnetic field, which is at a distance r from the midpoint of dl. And this magnetic field at P is due to the current element dl. And magnetic field at P, which is dB, due to current element IDL, which is at a distance r, is given by the Biot-Savart's law. According to Biot-Savart's law, the magnetic field dB is, or in other words, the magnetic field dB is directly proportional to IDL. It is directly proportional to the magnitude of current element. It is directly proportional to sine theta. And it is inversely proportional to 1 by r square, 1 by square of the distance between the two. According to Biot-Savart's law, magnetic field dB at point P due to IDL is directly proportional to the magnitude of current element IDL, directly proportional to sine of the angle between the midpoint of dl and the line joint. It is directly proportional to sine of the angle between the current element and the line joining the midpoint of dl and point P, and it is inversely proportional to distance between dl and P. Combining these two, we get dB proportional to, combining we get dB proportional to, after combining we get dB as proportional to ideal sine theta by r square. Ideal sine theta by r square. Ideal sine theta by r square. This is according to Biot-Savart's law. And after removing this proportionality constant, we introduce a constant mu naught by 4 pi, which is called the proportionality constant, followed by ideal sine theta by r square. dB equals mu naught by 4 pi ideal sine theta by r square, where mu naught by 4 pi is called proportionality constant, mu naught is called the permeability of a free space, and the direction of dB is same for all the current elements. This straight infinitely long conductor consists of number of current elements, and due to all the current elements, the magnetic field dB remains the same. The direction of dB remains the same. It will be along the same direction as shown in the figure. Therefore, in order to find the total magnetic field at point P, due to the entire length of the conductor, we integrate the above relation. We integrate this relation. With the limits of integration minus infinity to plus infinity, which is the length of the conductor. B is the total magnetic field obtained after integrating dB over the entire length of the conductor, and which is mu naught by 4 pi into integral minus infinity to plus infinity ideal sine theta by r square. Where from figure by making use of Pythagoras theorem, r square will be equal to capital R square plus L square, capital R square plus L square. R square is equal to R square, capital R square plus L square from figure. Yes. Also from figure, sine theta, or that is equal to sine 180 minus theta, this is 180 minus theta, that will be equal to opposite by hypotenuse, that is capital R by small r. Capital R is the same, whereas the small r is r square plus L square whole power half. Substituting for small r and sine theta in the above relation, we get B equals mu naught by 4 pi. We get mu naught by 4 pi. B equals mu naught by 4 pi into integral minus infinity to plus infinity. I will be taken outside as it is a constant. I is taken out. For sine theta, we have r. Divided by r square plus L square power 1 by 2, r square plus L square, r square plus L square power 1 by 2 into, we have 1 by r square ಒಂದಿದೆ ಇಲ್ಲಿ, but r square is nothing but r square plus L square, again, r square plus L square whole power 1, ಏನೂ ಇಲ್ಲ ಹಾಗಾಗಿ power 1 into dl. dl ಇಲ್ಲಿತ್ತು, ಅದನ್ನು ಹಾಗೆ ಕ್ಯಾರಿ ಮಾಡಿದ್ವಿ dl. This can be rewritten as equal to mu naught I by 4 pi, mu naught I divided by 4 pi, okay, into integral r dl, okay, whole divided by r square plus L square, whole power ಎಷ್ಟಾಗುತ್ತೆ ನೋಡಿ, this is half plus 1 and that will be equal to 3 by 2. Half plus 1 will be 3 by 2. This is the expression for magnetic field, not yet been integrated between the limits minus infinity to plus infinity. Same expression next slide ಅಲ್ಲಿ ಇದೆ, ಇಲ್ಲಿದೆ ನೋಡಿ, ರೈಟ್. ಸಿಂಪ್ಲಿಫೈ ಮಾಡಿ ಇಲ್ಲಿ ಬರ್ಕೊಂಡಿದ್ದೀವಿ. Now from figure L is equal to tan phi. ಇದನ್ನು phi ಅಂತ ತಗೊಂಡ್ರೆ tan phi will be equal to opposite by adjacent. Tan phi will be equal to opposite by adjacent ಆಗುತ್ತೆ. ಹಾಗಾಗಿ L is equal to R tan phi ಅಂತ ಬರುತ್ತೆ. Opposite by adjacent, L by R. Therefore L is equal to R tan phi. Or integrate or differentiating this, we get dl is equal to R secant square phi d phi. R secant square phi into d phi. ನೆಕ್ಸ್ಟ್ ಸ್ಟೆಪ್ಪಲ್ಲಿ ಸಬ್ಸ್ಟಿಟ್ಯೂಟ್ ಮಾಡಿದ್ದೀವಿ. ಫಾರ್ ಡಿ ಎಲ್ ಆ್ಯಂಡ್ ಡಿ ಎಲ್ ಎರಡಕ್ಕೂ ಕೂಡ ಸಬ್ಸ್ಟಿಟ್ಯೂಟ್ ಮಾಡಿದ್ದೀವಿ. ಏನಾಗಿದೆ ನೋಡಿ, ಇಟ್ ಇಸ್ ನಾಟ್ ಐ ಬೈ 4 ಪೈ ಇಂಟಗ್ರಲ್ ಮೈನಸ್ ಫೈ ಟು ಪ್ಲಸ್ ಮೈನಸ್ ಫೈ ಟು ಫೈ 1 ಮೈನಸ್ ಇನ್ಫಿನಿಟಿ ಇತ್ತು, ಅದರ ಬದಲು ಮೈನಸ್ ಫೈ 2 ಆಗಿದೆ, ಪ್ಲಸ್ ಇನ್ಫಿನಿಟಿ ಇದ್ದಿದ್ದು ಪ್ಲಸ್ ಫೈ 1 ಆಗಿದೆ. ಲಿಮಿಟ್ಸ್ ಹ್ಯಾವ್ ಬೀನ್ ಚೇಂಜ್ಡ್. ಆರ್ ಇಂಟು ಡಿ ಎಲ್, ಆರ್ ಇಂಟು ಡಿ ಎಲ್, ಡಿ ಎಲ್ ಅಲ್ಲಿ ಒಂದು ಆರ್ ಇದೆ, ಹಾಗಾಗಿ ಆರ್ ಇಂಟು ಆರ್ ಗೆಟ್ಸ್ ಆರ್ ಸ್ಕ್ವೇರ್ secant square phi d phi, right, whole divided by r square. ಹೇಗಾಯಿತು ನೋಡಿ, ಇದೊಂಚೂರು ಎಕ್ಸ್ಪ್ಲೇನ್ ಮಾಡಿಬಿಡ್ತೀನಿ ನಿಮಗೆ, ಇಲ್ಲಿ ಸಿಂಪ್ಲಿಫೈ ಮಾಡಿ. b equals mu naught I by 4 pi, mu naught I by 4 pi into integral minus phi 2 to phi minus phi 2 to phi 1 r ಹಾಗೆ ಇದೆ into dl which is r secant square phi d phi, r secant square phi into d phi whole divided by r square ಹಾಗೆ ಇದೆ. okay, no problem. Plus L square is r square tan square phi, r square tan square phi r square tan square phi whole power 3 by 2. Whole power 3 by 2. ಓಕೆ, ಇದೇನು ಪ್ರಾಬ್ಲಮ್ ಇಲ್ಲ. ಆರ್ ಇಂಟು ಆರ್ ಸ್ಕ್ವೇರ್ ಆಗಿದೆ, ಇಲ್ಲಿ ಏನು ಚೇಂಜ್ ಇಲ್ಲ. ಆರ್ ಇಂಟು ಆರ್ ಸ್ಕ್ವೇರ್ ಸೆಕೆಂಡ್ ಸ್ಕ್ವೇರ್ ಡಿ ಫೈ, ಸೆಕೆಂಡ್ ಸ್ಕ್ವೇರ್ ಫೈ ಡಿ ಫೈ ಹಾಗೆ ಇದೆ ವಿತೌಟ್ ಎನಿ ಚೇಂಜ್. ಡಿನಾಮಿನೇಟರ್ ಏನಾಗಿದೆ ನೋಡಿ, ಐ ವಿಲ್ ಶೋ ಯು ಓನ್ಲಿ ಸಿಂಪ್ಲಿಫಿಕೇಶನ್ ಆಫ್ ದ ಡಿನಾಮಿನೇಟರ್. ಆರ್ ಸ್ಕ್ವೇರ್ ಕಾಮನ್ ತೆಗೆದಿದ್ದೀವಿ, ಹೌದಲ್ಲ. ಇಫ್ ಆರ್ ಸ್ಕ್ವೇರ್ ಇಸ್ ಟೇಕನ್ ಕಾಮನ್ ದೆನ್ ಇಟ್ ಬಿಕಮ್ಸ್ 1 plus tan square phi, 1 plus tan square phi whole power 3 by 2. 3 by 2 ಎರಡಕ್ಕೂ ಬರಬೇಕಲ್ಲ, ಆರ್ ಸ್ಕ್ವೇರ್ಗೂ ಬರಬೇಕು. ಆರ್ ಸ್ಕ್ವೇರ್ ಹೊರಗಡೆ ತೆಗೆದಿದ್ದೀವಿ, ಹಾಗಾಗಿ ಆರ್ ಸ್ಕ್ವೇರ್ಗೂ ಬರುತ್ತೆ, ಹಾಗಾಗಿ ಅದನ್ನು ಬೇಕಿದ್ರೆ ಇಲ್ಲೇ ಹಾಕ್ಕೋಬೋದು. ಹೋಲ್ ಪವರ್ 3 by 2, ಹೋಲ್ ಪವರ್ 3 by 2. 2 and half gets cancelled. ಈ ಹಾಫ್ ಅಂಡ್ ಈ 2 ಗೆಟ್ಸ್ ಕ್ಯಾನ್ಸಲ್ಡ್. ಇದು ಆರ್ ಕ್ಯೂಬ್ ಆಗುತ್ತೆ. ಆರ್ ಕ್ಯೂಬ್ ಇಲ್ಲಿಗಿದು ಆರ್ ಕ್ಯೂಬ್ ಆಗುತ್ತೆ. ನ್ಯೂಮರೇಟರ್ ಒಂದು ಆರ್ ಸ್ಕ್ವೇರ್ ಇದೆ ಆ್ಯಂಡ್ ದೇರ್ ಫಾರ್ ಆರ್ ಸ್ಕ್ವೇರ್ ಗೆಟ್ಸ್ ಕ್ಯಾನ್ಸಲ್ಡ್ ವಿತ್ ಆರ್ ಕ್ಯೂಬ್. ರಿಮೈನಿಂಗ್ ದರ್ ವಿಲ್ ಬಿ 1 ಆರ್ ಇನ್ ದ ಡಿನಾಮಿನೇಟರ್. ಆ ಒಂದು ಆರನ್ನು ಇಲ್ಲಿ ಬೇಕಿದ್ರೆ ಬರ್ಕೋಬೋದು, 4 pi r ಅಂತ ಹೇಳಿ. ನೆಕ್ಸ್ಟ್ ಸ್ಟೆಪ್ಪಲ್ಲಿ ಬರೆದಿದೆ ನೋಡಿ, ಇಟ್ ಹ್ಯಾಸ್ ಬಿಕಮ್ 4 pi r. ಬಟ್ ಕಾಸ್ ಫೈ ಹೇಗೆ ಬಂತು ನೋಡೋಣ. ನೆಕ್ಸ್ಟ್ ಸ್ಟೆಪ್ಪಲ್ಲಿ ಸಿಂಪ್ಲಿಫೈ ಮಾಡ್ತೀನಿ. ಕಾಸ್ ಫೈ ಹೇಗೆ ಬಂತು ನಮಗೆ. ಈಗ ಅಲ್ಲಿರುವಂಥದ್ದೇನು, ಬಿ ಈಕ್ವಲ್ಸ್ ಏನಿದೆ ಬರ್ಕೋತೀನಿ, ಸಿಂಪ್ಲಿಫೈ ಮಾಡಿ. ಬಿ ಈಕ್ವಲ್ಸ್ mu naught I by 4 pi, mu naught I by 4 pi r, 4 pi r into integral secant square phi d phi, secant square phi d phi whole divided by 1 plus tan square phi whole power 3 by 2. This can be rewritten as constant ಹಾಗೆ ಇದೆ ಇಲ್ಲಿ ಆ ಕಾನ್ಸ್ಟೆಂಟ್ನ ಬಿಡ್ತಿದ್ದೀನಿ. there is constants over here. secant square phi d phi secant square phi d phi whole divided by 1 plus tan square is again secant square phi whole power 3 by 2 whole power 3 by 2. Therefore, again b equals the constant multiplied by or integral secant square phi d phi whole divided by e square root, e half gets cancelled, it has become secant cube phi d phi. Therefore, this becomes constant into integral d phi by secant phi. Sorry, ಇಲ್ಲಿ d phi ಇಲ್ಲ, d phi by secant phi, or this will be equal to some constant into integral cos phi d phi. Reciprocal of secant phi is cos phi. ಅದೇ ಸೇಮ್ ವ್ಯಾಲ್ಯೂನ ನೆಕ್ಸ್ಟ್ ಸ್ಟೆಪ್ಪಲ್ಲಿ ಬರೆದಿದೆ. ಇಲ್ಲೇ ಇದೆ it is 4 pi naught I by 4 pi r, which is constant, into integral minus phi 2 to phi 1 cos phi d phi. We have integrated cos phi. The integral of cos phi is sin phi. Applying the limits of integration minus phi 2 to phi 1, therefore b will be equal to mu naught I by 4 pi r upper limit sin phi 1 minus half minus plus sin phi 2. This is the final expression for the magnetic field due to a straight current carrying conductor at point which is at a distance r from the midpoint of dl. Okay, this is about the magnetic field, the net magnetic field due to the entire length of the conductor. Coming to the special cases, if the conductor is infinitely long and point P lies at the center of the conductor instead of point P over here, if point P is at point O itself, then these two become equal to 90 degree. Phi 1 will be equal to phi 2, which will be equal to 90 degree. Therefore, this is sin phi 1 plus sin phi 2, which is sin 90 plus sin 90, become equal to 1 plus 1. Therefore, mu naught I by 4 pi r into 2, or this is b equals mu naught I by 2 pi r, which is the magnetic field when the conductor is of infinite length and point P is at the center of the conductor, or otherwise P O ಹತ್ರ ಇದೆ ಅಂತ ತಿಳ್ಕೊಳ್ಳೋದೇನು ಬೇಡ. let P is very close to O, then for the infinite length of the conductor, this angle, this becomes almost 90 degree. ಹೀಗೆ ಬರುತ್ತೆ. This is almost equal to 90 degree. For infinite length of the conductor, it becomes 90. Right? Next, if the conductor is infinitely long, and point P lies near one end of the conductor, then what happens? If point P is over here, if this is point P, then illinda illige barutte, this is phi 1 will be 90 degree and phi 2 will be 0 degree. Phi 2 will be 0. This is phi 1, phi 2 ಹೇಗೆ ಹಾಕೋದು? ಇಲ್ಲೇ ಇದೆ ಲೈನು ಎರಡು ಪರ್ಪೆಂಡಿಕ್ಯುಲರ್. ಈ ಲೈನ್ ಮತ್ತು ಈ ಲೈನ್ ಮಧ್ಯೆ ಆ್ಯಂಗಲ್, ಈ ಲೈನು ಕೂಡ ಈ ಲೈನ್ ಥರನೇ ಇತ್ತು ಅಂತಂದರೆ ದೆನ್ phi 2 will be 0. They are parallel. Therefore phi 2 is 0 and phi 1 is 90. That is the case, mu naught I by 4 pi r into sin 90 plus sin 0, that is 1 plus 0. Therefore B equals mu naught I by 4 pi r is the magnetic field when point P lies at one end of the conductor. Similarly, we have a third case. If the conductor is finite length, not infinite, and if the length is 2L and point P lies at the center of the conductor, then let length of the conductor is taken as equal to 2L, which is finite, and point P lies at the center of the conductor, as usual. Then sin phi 1 will be equal to L by R phi 1, and that is equal to L by small r is root of r square plus L square that we have already determined, and sin phi 2 is similarly L by R, again L by root of r square plus L square. Therefore, B equals mu naught I by 4 pi r into sin phi 1 plus sin phi 2. That is the sum of these two. Since the denominators are same, the numerators can be added, that is L plus L, it becomes 2L. Therefore, B equals mu naught I by 4 pi r into 2L by root of r square plus L square. This is about the special cases of magnetic field due to a straight current carrying conductor. So coming to the multiple choice questions. In the Fleming's left hand, now coming to the multiple choice questions. The first question is, a current carrying wire in the neighborhood produces. What will be produced in the neighborhood of a current carrying conductor is our question. We have multiple answers. It produces both electric as well as magnetic fields. It produces only electric field. It produces only magnetic field, and no field is produced. The answer is, it produces magnetic field around the current carrying conductor. And the direction of the magnetic field can be determined by making use of right hand clasp rule. Second question, the magnetic field lines due to a straight current carrying conductor is. So in the first question, we said that magnetic field lines will be produced around the current carrying conductor. The second question is, yes, these magnetic field lines produced due to current carrying conductor is of different shapes. What is the shape of the head? It produces straight lines. Magnetic field produced by a straight current carrying conductor will be in straight lines, or will be in electrical, or will be in elliptical format, or will be the circular form, or all the above. These are the multiple answers. The correct answer is, a straight current carrying conductor produces circular magnetic field lines, and the direction of the circular motion can be determined by making use of right hand clasp rule. The thumb represents the current carrying straight conductor is assumed to be held in the right hand, such that the thumb represents the direction of the current. Then the encircled fingers, the four encircled fingers represents the direction of magnetic field around the straight current carrying conductor, which will be circular in shape. Coming to the third question, an electric current passes through a long straight wire. At a distance 5 cm from the wire, the magnetic field is B. Field at 25 cm from the wire would be, right? Field at a distance 5 cm from the wire is given as equal to B, and it is required to find the field at a distance 25 cm from the wire. So in order to find this, the expression that we know is the expression for the magnetic field is B equals mu naught I by 4 pi I mu naught I by 4 pi R mu naught I divided by 4 pi R divided by 4 pi R, where R is the perpendicular distance from the conductor to the point where we are measuring the magnetic field, multiplied by sine phi 1 plus sine phi 2. Sine phi 1 plus sine phi 2. This is our general expression for the magnetic field at a point due to a straight current carrying conductor. This is the expression. From this expression, it is clear that B is inversely proportional to R. B is inversely proportional to R. Therefore, B dash by B will be equal to B dash by B will be equal to R by R dash. That will be equal to R by R dash, as it is inversely proportional. R by R dash. That is equal to R is 5 centimeter, R dash is 25 centimeter, and that will be equal to 1 by 5. 1 by 5. Therefore, B dash is equal to B by 5 is the answer. B dash equals B by 5 is our answer. The magnetic field will be reduced by 5 times. B by 5. This is the new magnetic field, which is at a distance 25 centimeter from the wire. The option is C. Now, coming to the fourth question. A current I flows along an infinitely long straight conductor. If R is the perpendicular distance of a point from the lower end of the conductor, then the magnetic field induction is. As we know, the expression for magnetic field is B equals mu naught I by 4 pi R, mu naught I by 4 pi R by 4 pi R into sine phi 1 plus phi 2 sine phi 1 plus sine phi 2 at the lower end. Remember, it is said that the magnetic field at the lower end of the conductor, lower end of an infinitely long straight conductor. That is the problem given. At one end of the conductor, at the lower end, phi 1 will become equal to 90 degree, phi 1 will be 90 degree, and phi 2 will be 0 degree, and phi 2 will be 0 degree, and therefore this turns out to be equal to B equals mu naught I by 4 pi R, mu naught I by 4 pi R whole divided by, mu naught I by 4 pi R into sine 90 is 1 into sine 90 is 1 plus sine 0 is 0. Therefore, it is 1 plus 0. And therefore, the final answer is B equals mu naught I by 4 pi R, which is option B. And the fifth question. A current carrying conductor is held in exactly vertical position. This is the current carrying conductor. In order to produce a clockwise magnetic field around the conductor, the current should be passed to the conductor. In which direction it is to be passed? That is our question. If the current, if it is held in this way, such that the current is in upward direction, the magnetic field will be anti-clockwise. For the magnetic field to be clockwise, like this, clockwise, the current should be downward. That is from top to bottom. So, in order to obtain the magnetic field in the clockwise direction, the current should be downward. For anti-clockwise direction, for the magnetic field to be anti-clockwise, the current should be upward. So this is about